So welcome everybody to the second part of our workshop, first international workshop on semi-supervised continual learning. Today's session will start with the oral presentation from the Best Paper Award paper, authored by Lucas Caccia, who's going to present, and Joël Pinot. The title is Special Self-Supervised Pre-Training for Continual Learning. So Lucas, please feel free to start your presentation whenever you're ready.
Okay, thanks for the introduction. Yeah, so my name is Lucas, and today I'll be talking about learning representations with the specific goal of doing continual learning with them. And yeah, this is joint work with Joel, my supervisor. This work was done at the FAIR Montreal lab. Oops. Give me 1 second. Okay. Start again. Okay, there we go. Cool. So I'll first give some intuition of why we should care about learning. Then I'll talk about what kind of work was done in that field for continual learning. I'll proceed with giving some intuition about the method we're proposing, and then some early results followed by some ongoing efforts to scale the method up. So if you think about deploying continual learning models in real life, or just models in general, well, at some point you'll have to ask yourself whether or not you're facing a change in distributions, right? Because even in the most simple things like your social media feed, if you want to train to detect friends in your Instagram stories or your Facebook posts, while your distribution of friends or what they're posting is definitely going to change over time. So you'll want to be able to account for that. And in other uses like autonomous driving, if you bought a Tesla from California and you decide to drive it to Montreal in the winter, you're definitely going to be seeing new landscapes and most likely new weather conditions. So in a perfect scenario, you want to be able to modify your model with respect to that. And even just like user preference, whether it's for music or Netflix or recipes on Pinterest. And even though I'm changing taste, every once in a while, I like to go back to some stuff I was listening to in previous years and just listen to that for like a month before I move on. So those are the type of change that I like my algorithm to be able to model. So what we like is instead of every month training all the data we have so far, recreating an ID setting and updating model, is to be able to just deploy a model which can continually adapt to those shifts in distribution. So hopefully by now, I've convinced you that if you're going to deploy a model in real life, it doesn't really make sense to not pre-train it. Like whether you're working with vision or you're working with text, you can definitely find some like super large pre-trained model online. Almost call them foundation models, judging on recent Twitter trends. But if you have access to some data, you can probably find just a bunch of unlabeled data, which is pretty cheap to obtain, right? You just scrape the internet or find them, yeah, whatever works for you. And if you're gonna do pre-training, if you're gonna do pre-training, you can either do that pre-training, then fine-tune your model on the fly once it's deployed, or just keep everything fixed and train a small adapter on top of it to adapt to user-specific cases, for example. So the question now becomes, if you're going to deploy your model in a continual learning setting, how can you adapt the pre-training step so that this deployment is better or just goes more smoothly? That's the I'll be talking today with continual learning. Great. So our method builds on a lot of previous work. So I'll try to give a brief overview of those different components so you can get some intuition as to how we're tackling this problem. So the first one I want to talk about is MAML, model agnostic meta learning. So it's a meta learning algorithm essentially that allows you to train a model's parameters such that given a certain steps or given updates, you'll be able to converge fast to a new distribution. So the way it does this is by learning a good parameter initialization from which to start from when the model is deployed. And the computation is broken down into an inner loop and an outer loop. So in the inner loop, you're going to try to mimic the conditions that the agent is going to see at deployment time. So in our setting, since for us deployment time is continual learning time, well, in this inner loop, I'm going to try to mimic that by giving it some non-stationary data, for example, or some correlated data. And with this data, you're going to do a bunch of gradient steps on them to hopefully learn from that data. So here in this example, I'm doing 4 gradient steps, going from theta 0 to theta 4. And once you have this new model, then you reach the outer loop and you evaluate it on the thing you care about in your setting, right? So in our setting, since we're doing continual learning, I care about first, well, how well did I learn from the data I just saw? But more importantly, or more crucially, how well do I still remember stuff that I knew prior to doing those updates? Okay, so you have your initial model, you did a few updates in the inner loop, you have your final model, you evaluate on the meta loss, and then with this meta loss, you're going to back propagate through the inner updates all the way back to the original parameter initialization that you started the inner loop with, and you're going to modify that. And then with this new initialization, you're going to do another step on some new data, and so on and so forth. Yeah, so conceptually, you can kind of the inner loop as a test drive where you're going to simulate a deployment. You're going to get feedback telling you how to be a little bit better, and then you're going to start over with this new insight. Yes. Okay, let me skip over this in the interest of time. So now the question becomes, how can we leverage MAML to learn how to continually learn? So in a perfect scenario, what you would like to is within the inner loop, just mimic those conditions and run like split Mnist or split CFAR during this inner loop, and then reach a new set of parameters that will evaluate on, say, the held out validation set of the distribution you saw on like those 10 classes of Mnist or CFAR. However, you can't really do that with MAML because unrolling the computational graph for hundreds or thousands of time steps is just not feasible from a computational perspective. So you need a way to come up with a meta learning objective, which can simulate continual learning deployment in a manner. And that's not a trivial thing to do. And that's and actually the online aware meta learning paper from Khurram Javed and Martha White, they come up with a really neat trick to do this. So the way they do it is as follows. So in the inner loop, they feed the model like this sequence of correlated points, like a bunch of samples from the same class, for example. And then in the outer loop, they're going to evaluate for 2 things. Just like I said before, like how well did I learn from these samples in my inner loop, but also how well do I remember those classes that I knew prior to entering that inner loop. Yes. Okay. So let's go through an example. I think it's easier to understand with the actual pretty images. So say this is your, so in the inner loop, you're going to see a bunch of correlated data points. So at every step in the inner loop, the model only processes a single example, really to mimic those online conditions. So yeah, in this inner loop, at every step, you're going to see a pretty image of a crab. Before I explain the inner loop, it's actually easier to move to a few iterations. So what kind of data the model sees. So say the second iteration, I see a bunch of Dalmatians, and the third iteration, I see a bunch of lions. So once I reach the inner loop here, I want to check first, how well did my model learn about lions? And we can see that reflected in the outer loops because I see a bunch of lions. But crucially, and this is really the key point here, I'm also presenting the model with images from previous distribution that I saw in previous inner loops, where you can see Dalmatians and a crab here at the end. And for a model to minimize this objective well, it really needs to learn without forgetting, because it needs to learn about what it just saw, but also remember stuff from previous inner loops. And that's really the key insight from the OML objective. Great. Yeah, so another thing they do from a purely optimization perspective is that, unlike MAML, where once you deploy the model, you're going to modify parameter with gradient updates, just like you would in a regular model. What they do here is, during the inner loop, they're actually going to keep part of the network frozen. So here, the part in blue throughout the loop and outer loop is the same. It doesn't get modified. It only gets gradient from the outer loop signal. And what this allows you to do, what they show is, it just leads to better results because optimization is easier to handle. And crucially for us, as we'll see later on, the part in blue can be parallelized. Since it's kept the same across all the inner loop and the outer loop, you can run all this feature extraction step in parallel, which will come in handy. Okay, so in terms of results, they actually have some pretty surprising results for the time, where if you compare it to just like regular pre-training, were you to deploy a model with those learned representations, it actually does a lot better. And they do most of their investigation on a data set, and they can show like the model can learn like up to 200 new classes that it didn't see during training, and get pretty reasonable accuracy with it. Okay, so to recap OML, what they do is they manage to create a meta objective which promotes continual learning by feeding small correlated sequences of points in the inner loop and evaluating for retention on both old and new classes. So what's really cool about this is it's a data-driven way to learn an inductive bias. Like, I'm not telling the model what I think the representation should look like. It just learns representations which work for this setting. And as we just saw, like those representations, they seem to transfer well to new classes of a distribution that's similar to the ones that were used for training. So on other things that we'd like to make better, so this is a fully supervised algorithm, right? I need labels from start to bottom. So if I want to leverage unlabeled data, I'll need to come up with a way to remove this need for labeled information. And the other thing is, because we're doing this sequential inner loop where, like this red part of the network I was showing before, right here, gets unrolled at every time step. Training is not, it's hard to parallelize because of that. So we'll try to address too. Yes. And the last part I'll be discussing today as preliminary work is work on self-supervised learning. So in the context of images, self-supervised learning is a way to learn image representations without the need for labeled information. So what I'm showing here is kind of the core idea of contrastive methods, where you're going to take a bunch of unlabeled images, and for each of those images, you're going to do multiple stochastic augmentations of that image, and you want to learn a representation where different augmentations, but of the same underlying image, end up close to each other. And the way you do this is by having a loss which pushes, so in this example, like these two augmentations dock together, and it repels them from the augmentations of the couch. And in terms of results, I think now you can pretty much learn representations that are about as good as fully supervised representation, and maybe a bit better for some downstream tasks. So yeah, the literature is getting pretty mature for this type of feature, for this type of unsupervised learning of representations for images. Okay, so hopefully now you have some intuition as to how the OML algorithm works. And yeah, now the next step is how can we go from OML to the method we're proposing, special, which is the yeah. So we do two things essentially: is we make it unsupervised and we investigate how to scale the method up, make it more computationally efficient. Okay, so the first challenge is removing the need for labels. And just like you saw in the GIF of the self-supervised methods, we're really just taking a page out of the book and using different augmentation of the same underlying image and attributing all these augmented image from the same underlying image, the same label. So to give you an example, in OML, what you would do in the inner loop, like draw a bunch of images from the same class to get this correlated data sequence. Here, what we're going to do is from an original image, just draw a bunch of augmentations on that image. And since they're drawn from the same original image, it follows that they're obviously very correlated. So that's the first step, the probably easier one. The second thing we want to address is how can we scale this method up? As we saw, there's a few things that we'll need to address. We essentially three big modifications, which allows us to, instead of modifying in the inner loop like the last few layers of the network, we're actually going to bring this this part that gets updated in the inner loop, like the red part of the model I was showing before, as small as possible. So what we mean by this is only the last linear layer of the model, the one that does classification, is going to be modified in the inner loop. And what this means is everything before that, we can actually run in parallel, which is really good for to make things faster, right? So even if we're unrolling the last linear head for like 16 time steps, it's very cheap to do so because in a regular model, that linear head accounts for less than 1% of the total flops of a forward pass. Great. So the second thing we're going to do is we're going to batch the inner loop. So in OML, when you're processing the inner loop, at every step of the inner loop, you're only processing one image. And what we're going to do is we're going to take a bunch of sequences actually and process them in parallel in the inner loop. So say you have 10 sequences of image. Here at every step in special, we're going to be processing 10 image, one for each sequence. And what this allows us to do is just to process more images given the same amount of time. And the last thing and most important thing we're going to do is we're going to cache past computations for rehearsal. So remember how in OML, to make sure you're learning without forgetting, you would basically just draw random samples that from distribution from the distributions you saw in previous iterations. Here, we're not going to do that. We're actually going to just keep a small queue where we store hidden representation of past iterations instead of raw image. And we're going to be sampling from this small queue to get some information about past distributions to make sure we're learning without forgetting. And this part in OML, this forwarding of rehearsal points accounts for about 30% of the compute. So that's what we're saving by doing this caching. Great. So here's an overview method. It's a bit of a, it's pretty condensed. So let me go over it with you guys. So first thing you do is you're going to receive some data that's displayed here in the incoming batch. And what you're going to do with this data is generate a correlated sequence of points, which is shown here under the inner loop sequence. And you can see it's correlated, right? Because every other image comes from the same distribution as the one just before that. I see some people in the chat. Let me just check that I'm not like muted or anything. Okay, no, I have 5 minutes left. Cool. Yeah, let me just do that. Okay, cool. So where were we? Yeah, so you generate a sequence of correlated points. And just similarly, in the outer loop, you're going to be drawing new augmentations from the same underlying images, where I'm showing here. And what we're going to do is we're going to process all these images in parallel through the network base to get features. And those features are shown in those 3D rectangles here. Every color denotes a label, basically. So once we have those features, this is where the inner loop starts, where we're going to be training our linear head, our linear probe sequentially on top of these features. And what you get is, so here we're going to do that for 6 time steps, get your final parameters for the head. And then once you reach the outer loop, just like OML, we want to evaluate 2 things: how well you know the stuff you just saw, which are shown under the label outer loop, those 3 samples, but also how well do you remember stuff you saw in previous iterations, and that information is kept inside the is essentially how well can you classify those representations from previous iterations. And those representations, we're just sampling them from a queue to which we're adding the representations from the current inner loop after the training is done. So you just get a feed of recently seen features. Okay, so I'm still stuck. Okay, there we go. Yeah, let me skip over this. So how do we evaluate our representations? We're gonna take this evaluation protocol from OML, and what they do is they generate a stream of correlated points. So what they do here is you're essentially going to see 30 samples per class, 1 at a time. So you have this stream where the first 30 samples belong to the same class. Then the 31st sample all the way to the 60th sample is going to belong to a new class. And you're going to do that for, say, 20 or 50 classes. So it's really just 1 sample at a time and 1 class at a time. And the thing we care about is how well can our model classify these new points from classes it hasn't seen before. So we're going to be evaluating it on its test accuracy of, just held out points from the same distribution of those samples. So these are some preliminary results where here we're using an architecture that's very similar to the one used in the OML paper, which is like a relatively small convolutional neural network. The only difference is we're using a skip connection, which really helps the optimization process. So what we see here is that, well, it's pretty encouraging, right? Like the fully unsupervised method special can actually reach a performance that's very similar to what OML is reaching. So, and it can do that without using as much compute, which is definitely a good thing. Yes, so now we have, some preliminary results which suggest that this seems to be working. And to me, once I knew this, the next step was really, can we scale this up? A lot of the self-supervised literature really focuses on, just larger scale experiments. So I was really curious to see if we make things better, what kind of results we can get. So yeah, the answer to can we scale this up is yes, to a certain extent. What I'm going to show here is results with a small vision transformer. We're going to make the images a bit bigger, and we're going to use twice as many GPUs. And if you compare to other self-supervised learning methods, which also do relatively good, I think it's worth pointing out, we have some gains in terms of final performance on a downstream continual learning task. So this really shows that if you know that you're going to do continual learning when the model is deployed, it makes sense to incorporate that information in the pre-training step. Okay, and the last thing I'm going to mention today is how does this affect training time, right? So we're unrolling a sequential optimization process for 16 steps. It's really unclear that you can do this in an efficient manner But if you look at the training time, since we're only modifying this like last layer in the network, it actually comes at a pretty reasonable cost. If you compare to SimClear, which uses a similar amount of forward passes through the model, we're only doing like 15 minutes more over 11 hours, which I think is a valid trade-off. Okay, am I out of time? I think I have like 30 seconds left. Yeah, let me just skip over this. If there's no questions, I can talk more about this, but yeah.
All right, then. Thanks for your very nice presentation. And I'll leave the floor open for questions at this time. We have a few minutes before the poster session starts, so. Oh, I'll start with one. So I was wondering if you have run any analysis of the influence of the ordering of the classes in the outer loop or the samples in inner loops. Does that matter in any way?
That's a good question. I haven't done any. So what I can tell you about this is I personally don't think the ordering matters that much. What seems to matter is how you split the inner loop sequence. So for example, if you're going to do 10 steps, you can either do 10 step on a single class, or you can do 5 steps on 2 classes. And what I'm seeing is for OML, the fully supervised method, it gets better results if you do like one super long sequence of one task, whereas for our method, the unsupervised one, it does a bit better if you split it over multiple images.
And what about the duration of the inner loop? I understand this is like a few-shot learning framework, but how does the performance depend on the duration of the inner loop?
So the longer your inner loop is, for the supervised case, usually the better the results are. Obviously, the longer your inner loop is, the longer training takes. So you need to strike this type of trade-off. But for the unsupervised case, the gains from using a longer sequence don't seem to be as big. It seems like if you're kind of stretching it, you're kind of stretching it a bit, since we're not really using labels, right? Like if you're drawing 20 augmentations of the same image, you're not going to have as much information in those 20 images as just 20 images from the same class, but that are inherently different images, right?
Does that mean that like that saturates as a function of the number of augmentations, basically?
Yeah, that's a good way to put it.
That's interesting. That's interesting. And thanks for that. Any other questions before we start the second poster session? Don't be shy, as usual.
Well, maybe I'll give one. Very nice work, Lucas. I really liked how you kind of take inspiration from both OML and as well as like the self-supervised type of approach. So I'm just like, a lot of the work that we see, it's just focused on the classification problem. Have you thought at all about how you can scale some of these techniques up to other, let's say, vision tasks? So segmentation, for example, or detection?
That's a good question. So in terms of OML, if you have those segmented labels, you can definitely try to run it. And I like to think that would work reasonably well. In terms of our method, it's like you need a way to generate labels, right? So generating labels for segmentation, maybe there's a way, I'm not sure. Maybe there's like a way you can piggyback on some initial prediction and just try to leverage that. But that'll be the crucial challenge. So like if you think a bit about it, like MAML is a super general algorithm and it can do a bunch of things. And then OML just like refines it a bit to the control learning setting. And here the cost of not using labels, I'm like refining it a bit more to like the vision task. So Yeah, so that's kind of the trade-off I'm making. So if you can come up with labels for tasks like segmentations, I like to think that you can do something similar and make it work.
Yeah. Okay, thanks for that.
Cool, thanks for having me.
All right, then I'll, if there are no more questions, I'd like to thank our speaker again, Lucas, lead author of the Best Paper Award this workshop. And I'll stop recording and I'll invite you all to join the second poster session right around Red Room 4. So see you in, after that, sorry, we have a coffee break. So we're going to be back to the Zoom session at 15:50 UTC with the third invited talk by Tina and Tweeted Eyes. All right, then I'll stop recording now. So I'll leave the floor to my co-chair, Vincenzo Domonico, who will introduce our invited speakers for today.
All right, welcome back. So today we have the pleasure to host Tine Tuitelaars. She's a professor at KU Leuven in Belgium, and without any doubt, one of the leading actors in computer vision, pattern recognition, and machine learning worldwide. She is the author of several seminal and pioneering works in deep continual learning that have been, I think, instrumental for the recent surge of interest in this field. And she was recently awarded with the NERC Consolidator Grant on Continual Learning, one of the most prestigious grants in Europe for fundamental research. So we're very excited to hear new thoughts on this area from Tine, and thank you for being with us, and feel free to start when you're ready.
Okay, thank you, Vincenzo, for having me. So let me first describe what I intended to do with this talk. So I'm not really focusing on any recent work or one specific contribution. I guess you can see those at the relevant workshops and conferences as such. I took the opportunity of the invited talk to more take a step back and think a bit, okay, what's the current state of affairs? Where have we got? Where are we going? Where should we be going? And want to share those with you. And so, yeah, the title is not very informative, Continual Learning, Some Random Thoughts. And indeed, I focus on deep continual learning, since in our work, we always focus on continual learning in a deep learning context. And so with the risk of saying a few things that might be obvious to some of you, I think, or I hope that at least some of the ideas might be thought-provoking and helpful for other researchers. Okay, so so continual learning has actually gained enormous popularity in recent years, like within the deep learning and computer vision communities, where my background is. We see indeed like an enormous growth of attention to continual learning. I guess all of the major conferences these days have a workshop dedicated to continual learning. And I think if you start wondering why that is, the answer is that actually continual learning holds the promise of solving some of the core limitations of deep learning. It's now about 10 years that we're all very excited about deep learning and all the breakthroughs that it has brought to us. But at the same time, if you ask around, there's still like core limitations to these methods, especially when you go beyond the academic setting of just dealing with benchmark data sets, but you want to bring it to practical applications. And I think this could be the top four. When you want to deploy a deep learning model, you need to have large amounts of data. And so in any practical application, the first thing you would have to do is to collect all of this data, annotate the data, clean up the data, make sure it's nicely balanced and such, which actually is an almost impossible task. The world has all these long tail distributions, and so waiting until you have enough examples of all these rare events could take forever, and that makes it really hard to replicate these successes that we have on these nicely curated data sets like ImageNet and whatever to real world applications. Second, and highly related to this, there's the lack of generalization that people often get frustrated about. The model is only as good as the data, and if so, you might be lucky and find some public online data set that has a lot of object categories that you're also interested in. Even then, just taking a model trained on that data may not perform as well on your own data because there's still a distribution shift and the models cannot cope with that. Third, models are specialized for a single task and so very dedicated to a task. If you want to change something about the task, extend it, whatever, you run into problems. And fourth, but I put that between brackets because it's less relevant here, I guess there's still a lot of people who would say the major limitation of deep learning is that it's just pattern matching. It's not really doing anything intelligent like human intelligence or whatever. Now that's kind of a completely different discussion. And so that's why I put it between brackets. But for the other three, if you look at most introductions of continual learning papers, then it seems that, yeah, continual learning is gonna solve it all. And so all these open issues we have with data sets, generalization, and so on, if we have a good continual learning system, actually we can start training our model and keep adding data as it becomes available. And so these long tail distributions are no longer a problem. We can start from public data sets and then adapt them along the way. If these models work well and they also have forward transfer, then we don't need as much new data to learn a new category or a new domain as we would otherwise. And so we can change tasks, add multiple tasks and so on. So it seems like, yeah, the one thing that solves all of our issues. And that's why I guess a lot of people gained interest in it. But of course, that's a very ambitious goal, and we're still far from reaching that goal. And so that's why I want to say, okay, where are we now? And indeed, where should we go from here? If we look at continual learning in action over the years, we actually started by looking maybe at rather toy problems like split Mnist or even permuted Mnist and things like that, and try to really gain insight in this learning dynamics. And that's what initially drew my interest into this field, because I found it very inspiring how to understand continual learning, we actually don't just take an architecture as a black box, put data through and then just tweak it and so on. No, to understand continual learning, you really have to look into the learning process and start thinking about, okay, what's the effect if our data is not just a single distribution, but has different modes that basically optimize different losses in our parameter space that basically pull the optimal solution towards different local minima. And so there was nice works trying to imagine what these loss surfaces look like and approximate them, so that if you know what this loss surface looks like, you can exploit that information when learning a new task. So that's what elastic weight consolidation did. there's works reasoning about these different gradients where each task basically pulls the current solution to a different, in a different direction. That's this tug of war game that's going on that Razvan always refers to. And thinking about how these gradients interact with each other and how we can actually try to compensate or change the learning process to deal with these differences is very appealing by itself. And so this is a possible solution based on gradient episodic memories. And the final figure is from one of our own papers, which will appear at ICCV, where we also try to visualize these loss spaces and the trajectories of how learning actually takes place in these huge dimensional parameter spaces. And so for me, this was really very rewarding to think about it like this and try to really understand what's going on when we learn a model and how, what are the dynamics there and how that affects actually the final solutions. But then again, if you look in practice, the best solution we have to date is kind of disappointingly or frustratingly easy. The best thing we can do is to say, okay, let's just keep a buffer, store some samples in that buffer and replay those, and that's it. So it is very simple, and by itself it's nice that the simple approach actually gives state-of-the-art results. At the same time, it remains unsatisfying because it's like, yeah, isn't there anything better we can do than just storing a buffer? Because if that's all there is to continual learning, then no way is this going to solve all these deep learning problems we had before, because at best it will mimic the joint learning setting, and then it will go back to, you need all the data nicely balanced and representative and so on. So I guess we're still hugely away from this vision that we have of what continual learning should be. And so there's still a lot of research to be done in that direction. So then the question is, how do we proceed from here? We have on the one hand something that works reasonably well, on the other hand more theoretical things and analysis, but no real solution there. My first advice there would be, okay, maybe we shouldn't be too ambitious. We typically aim for the impossible. We want to have a solution that doesn't forget, that does not increase the memory, that can deal with an infinite sequence of tasks, where you have forward transfer, where you have backward transfer, where you never revisit old tasks, where you learn everything from scratch, ideally from streaming data. And that's just so much that we don't know where to start, and it's difficult really to tackle the problem. And so we see that in the literature, we start to have these two flavors of continual learning. That is, on the one hand, we have the academic setups, like that really say, okay, let's do it in a very formal way. Like we have task incremental learning, we have class incremental learning, domain incremental learning, and we clearly define how we set up the experiments. And maybe this is somewhat toyish and not the real problems, but at least we have proper formalism and we can more easily have a theoretical analysis and we can compare methods and so on. And then on the other hand, there's a thread that says, okay, let's focus more on practical setups. Indeed, these academic setups can be criticized in many ways, because whenever you have a practical problem that you want to solve with continual learning, then your data typically will not be as nicely balanced. This idea that you have tasks that are mutually exclusive is maybe not very realistic in practice and might actually make it harder than needed. As we have also heard in the previous talk, it doesn't really make sense from a practical point of view to always start from scratch. You could have a warm-up phase, or you could start with some pre-training phase and have a good representation already to build on. You want probably to go beyond just classification. There's a lot of practical settings where you want to do detection, segmentation, whatever. And classification as such is not so common in practical real world problems. And you want to scale up. It doesn't make sense to do continual learning if your data set is really small. It only makes sense really when there's so much data that there's no way you can store it all together. And so I think what we see a lot is papers where they just say, okay, we criticize the academic setup and we just pick one of these things and move a bit in that direction, propose a solution there. And while I agree that, yeah, they have a valid point and these practical setups or these practical problems are the ones that ultimately we want to address, it does make it harder to actually value the contribution of an individual paper, because it's harder to compare things, to compare results, to see whether what are the baselines, where things are really we're really making progress or not. And so I really think that we still need to have research really in both directions. On the one hand, we need to reconsider the academic setup, the very simple toy setups. And even though we know they're not perfect, let's see what we can do there. And let's use these setups to gain more theoretic understanding of the learning process as such, and try to come up with really innovative solutions there. While in parallel, we can work on more practical setups, and probably in the first instance, these two directions may diverge a bit, but maybe at a later stage, again, ideas from the more theoretical analysis could be applied in the other thread. So concretely, when it comes to the more academic setup, I advocate that we should really rethink some of the basics, or actually not just some of the basics, but all of the basics. Maybe we're a bit naive in thinking that we could just take all these tools that are highly engineered and developed over years for the IID setting and just think that we could use the same architectures, the same loss functions, the same activation functions, the same optimization methods in a non-IID setting. The difference between IID and non-IID is so fundamental that probably it affects lots of different aspects in the learning process. And a lot of the design choices that have been made in standard machine learning, standard deep learning, that are optimal in that setting may not be the right choices for a continual learning setup. And so I think we should go back to the drawing table and kind of carefully check the underlying assumptions and the processes that take place when you actually go from an IID setting to a non-IID setting. And I think we would be surprised about how many things basically rely on this IID assumption and should actually be adapted or reconsidered. And hopefully that gives us a better position to then tackle the real world problems as well. When it comes to the practical setups, I really am a big fan of all these challenges, like the one at this workshop, because it has multiple benefits. It makes additional data sets available, typically more realistic practical data sets. It allows directly to compare different methods on those data sets, and it focuses on specific aspects, indeed moving beyond this toy setting that we have in these more theoretical works. And so I want to abuse this occasion to advertise another challenge that we had at the workshop at ICCV. So that's basically a workshop on semi-supervised learning for autonomous driving. And so at first you might not consider it if you're working on continual learning, but there we also have a track of a challenge focusing explicitly on continual learning in the context of autonomous driving, where you have different domains because there's like different cities, different weather conditions, different time of the day, different environments that all cause distribution shifts, and we can have really natural distribution shifts. So it's not this mutually exclusive artificial setup, it's a chronological shift over time that we can consider. And so we have one track where we focus on object detection in a task incremental setting, and one track where we focus on classification. So basically bounding boxes are given and you just have to figure out which class these bounding boxes belong to. And that's in a streaming fashion, which brings its own challenges. And indeed, we noticed when setting up this challenge, there's a lot of things that are still overlooked these days, like imbalance between categories that also changes over time. Like you see hardly any pedestrians at night or on the highway. And so this is some kind of dynamics that you have in continuous learning that didn't actually get a lot of attention so far, but leveraging good ways to dealing with this kind of changes in the prior for different categories might actually be really important in this setup. And finally, I also think it's, I want to advocate more work on learning from streaming data. So when you think about the ultimate continual learning agent, then it probably doesn't process one task at a time, but rather just processes the data as it comes in. And so it's something that we started looking in more closely, because it's a very natural way of learning. But it brings typically an extra challenge in that you see each sample only once. And so that means that you cannot revisit the same sample, you cannot do multiple epochs over the sample. And so you need to basically try to get as much information out of that sample as you can, especially if it's like a sample that belongs to a rare or underrepresented class. And so what we typically do, which is like just taking one small gradient step in the right direction, clearly is not enough in that setting. So there's must be ways to extract much more information from there. And this kind of push us towards looking not working with explicit classifiers, but rather reasoning with prototypes in an embedding space, because just a single sample can already give you the exact prototype or a good approximation of the prototype. And so that's a much more direct way of learning things than doing it, starting from a random initialization and taking tiny steps each time. Now, when I looked at some literature on working with streaming data, I found this review from Zhao Gamma, which kind of I found interesting to share. So this is about learning from streaming data in general, not specifically focusing on deep learning or continual learning. And in that survey, a lot of methods are tackled, like just linear classifiers, decision trees, shallow networks. But there's only very little information on deep learning from streaming data. And the reason that's given there is that basically deep learning is just not suitable for dealing with streaming data for two reasons. First, it's too computation intensive, like you need big GPUs and whatever to train. And second, it's too sensitive to hyperparameter settings. And so this is a different community, and I don't think there's sufficient interaction between these communities, but they kind of say, okay, deep learning is not the way to go. We see that indeed there's a trend to say, okay, let's focus just on the last few layers, and then it already becomes more feasible. They have specific solutions to tune hyperparameters on streaming data in an online setting, but then again, not to the scale that we would need it for deep learning. But there again, I think maybe we are just too ambitious if we say we want at the same time to solve this computational complexity together with solving the fundamental problem. When we say, okay, we only take one gradient step per sample, that's because we think, okay, we have to be fast. If we deal with streaming data, we automatically think there's like 25 frames per second. And that means there's very little time to analyze each and every sample. But I advocate for something that I rather call slow continual learning. That is, instead of considering 25 frames per second, what if we would have something like 1 frame per hour, or maybe 1 frame per day? That's also continual learning. That's also learning from streaming data. But at least for now, let's take away this constraint that we should be extremely efficient and we don't have any time to really analyze things in detail. And I think it's an interesting thought experiment, what we actually, how we would solve or tackle the problem if we had all the time we wanted. So you have the time to do much more computations. And so instead of just computing the gradient, which is like a first order approximation to your loss surface, why not try to get a second order or higher order approximation of your cost function? Why not add data augmentation and have multiple forward passes? Why not take more steps? Ultimately, you could say, I can sample the entire parameter space and compute the gradients in all these possible locations. And then I have all the information that I might possibly need later on. But of course, again, we cannot store all that information. So that's not an option. You could think about taking the sorry, I lost my. You can do it in lots of different ways, but it's yeah, an open question I have, and it's just an indication where I say, okay, maybe not solve everything at the same time. Let's do it step by step and slowly move towards this goal and make sure that we really understand what we are doing and how things are actually working. I guess that was all for me. So if you have any questions, then please go ahead.
Thank you, Tina, so much for your talk. I think it was much more than some random thoughts. So thank you so much for that. It was very informative. And so let's see if we have some questions in the chat. Otherwise, I have a couple, even though we have just a few minutes before.
I would like to say something for sure, because Tina touched upon a number of things that are like the foundations for this challenge that we try to propose this year. Things like focusing on streaming data and the importance of the ordering, like the data in the real world come from with a certain order, so it's not artificial like in the current benchmarks. That's exactly what we wanted to have with these two new benchmarks on continual activity recognition and continual crowd counting, where the ordering comes from the videos that are acquired. It's not set by the researchers in any way. It's a move in our mind. It's a move towards large scale, away from toy data sets like Mnist and all these other little things that people have been playing around. It's a move to beyond classification towards regression, because one of the two challenges is a regression challenge, because the task there is to regress a density map that corresponds to the head, to the people and the video frame. And also it's a combination of pre-training and continual learning from a data stream, because the inspiration from all that comes from real world problems that the industry has to face. And there you have a lot of time to do pre-training on large data sets to start with. And then only at deployment time, you need to deal with streaming data, and typically unsupervised streaming data. And that's why we call this semi-supervised learning, but not just a random mix of supervised and unsupervised samples, but the supervision comes all up front at the beginning. When you have large machines, you can do as much supervised learning as you want. And then the unsupervised part is the streaming part, and that comes after deployment. So that all these objectives that you mentioned in your presentation are very much at the center of all these challenges that we're presenting here.
Yeah, so I must say, when we started thinking about the challenge, so for the ICCP workshop, because the workshop is also about semi-supervised, we considered of also doing it semi-supervised continual learning, but thought like, yeah, maybe it's too challenging for now. Let's first have one track on semi-supervised, one track on the continual learning part. So again, trying not to be too ambitious from the start, but yeah, from your challenge, there's already pretty interesting stuff that comes out, and so yeah, I agree that this is the direction to go, because if you have streaming data, it also comes a bit unnatural that you have the supervision available. So it's not as if you have an oracle that just in a streaming fashion provides you with labels at 25 frames per second. So indeed, streaming data probably goes hand in hand with more unsupervised setups. So yeah, I think that's definitely for the practical setting the way to go, but I still think we also need to have the more theoretical things, so the two side by side.
Absolutely. So I think that we don't have time to go through all the questions that have been coming here in the chat, but I think we can read one more.
Yeah, we can
at
have
least,
one or
then,
two and then sacrifice a little bit of the time. I mean, we are having the debate as we speak anyway.
Yeah,
so.
exactly. So I wanted to invite all the people that are asking questions now to just wait a little more, and after the next imminent talk, we will have the panel where we can discuss about all these different topics. So Tina, there's one question here that is from Lucas Kacha on that train of thought. Do you think there is some way to leverage the inherent ordering of streaming data to actually do something better than IAD training?
So I guess you're referring then to curriculum learning setups, where you kind of start from easier tasks and then gradually fill in the details and make it harder and harder. I'm a bit mixed there. So in theory, curriculum learning sounds great. In practice, in my own experience, I haven't really observed big gains by going from easy to hard, and then just, yeah, IID data typically seem to be the most straightforward thing to do. But then again, it probably also depends on the actual setting and so on. And if you say you learn from streaming data, yeah, if we assume that you don't have control over the data, then you just have to take it as it comes. I guess that's a kind of implicit assumption that we at least usually make, that you don't have control over it, because if you have control, then probably, yeah, you could also just shuffle and make it IID or something. Don't know whether that answers your question.
Let's hope it does. Otherwise, Lucas, you can also. No, I don't know if he can open the mic here, but.
Sorry, Vincenzo, I'm gonna come back to this for the debate, because this is something that I'm really keen on, and this is also part of the concept that we're trying to propose here.
All right, perfect. Lucas says that he will keep it for the panel. All right, okay, I see that Chelsea is already here. Hi, Chelsea. Can you unmute yourself? I don't know if you can. Yes, you can. Yeah. You can also try to share your screen. Okay, we can see it well. So let me just present Chelsea. Well, Chelsea Thin is an assistant professor at Stanford University, where she leads the IRIS lab, working on artificial intelligence through robotic interactions. And Chelsea is a world-renowned researcher in the context area of meta learning, continual learning, and robotics. And we are very excited to hear from her recent thoughts and recent works in this area. So thank you so much, Chelsea, for being here with us today. And feel free to start when you're ready.
Great, thank you for the introduction, and also happy to take questions at the end of the talk. So part of my motivation for studying continual learning is that I think that there's a bit of a gap between our current and more standard paradigm in machine learning and a lot of the problems that we face in reality. In particular, I think that our current paradigm in machine learning research is to take a data set, train a model on that data set, and evaluate that model in a fixed fashion on your test set, maybe. When in reality, the world is constantly changing, whether it be things like stocks or supply and demand changing over time, or even as an agent kind of interacts in more parts of a very large world, it's going to be encountering situations that are changing over time. And so I think that this kind of necessitates algorithms that can handle the fact that the world is changing, rather than trying to deploy a fixed model in a changing world. Now, one solution to this challenge is that we could simply just continuously fine-tune the model. And this has worked super well. We've seen pretty great numbers, both in computer vision and natural language processing, when we try to fine-tune in comparison to training from scratch on the new domain. And also more recently, we've also found that in robotics, you could also do the same thing. You can pre-train on one environment and then fine-tune using reinforcement learning in new environments and allow the success rate of a state-of-the-art robotic grasping system to increase substantially, even though we've changed the environment drastically, including shifting the gripper 10 centimeters. So fine-tuning does seem like a pretty compelling alternative in the realm of deep learning for adapting models to changing scenarios. However, fine-tuning also requires a non-trivial amount of labeled data. And so what I'd like to talk about today, and also in theme with the workshop, is whether we can allow neural networks to be adapted online using only unlabeled data. And if we could do this, then we could probably much more readily capture the changing world, because we won't actually need a human labeler or other supervision in the process of this adaptation. Now, of course, if we adapt using unlabeled data, we don't necessarily know exactly how we should adapt and how to align that unsupervised adaptation procedure with the task at hand. And so one strategy that I'm going to be talking about today is whether we can learn how to learn these unlabeled adaptation strategies using meta-learning. And this essentially allows us to ensure that the unlabeled adaptation strategies are particularly tailored for improving at the task at hand and handling the kinds of distribution shift that the world throws at us. And so what do I mean by this? Well, I'll give a quick example of how meta-learning works. In particular, we typically assume that we have a small data set, that we have a few examples that we want to adapt to, and we want to be able to learn from these 5 examples in order to classify new examples. And so we have this very small training data set. We want to use this to be able to generalize to new examples. And the way that meta-learning works is, well, if we just fine-tuned on these data points, we probably would overfit because it's a very small data set. But what we can do is we can essentially structure existing data into train sets and test sets, just like the kind of adaptation we want to be able to do to a new task. And so we'll essentially train a model such that after it sees one of these training data sets, it can generalize to new examples. And so this is kind of this learning to learn process that we perform on these training classes so that we can then at meta test time adapt with a very small amount of data. Now, of course, meta-learning can only, this example of meta-learning is a labeled adaptation scenario where we're adapting to labeled data points. But it's worth mentioning that you can replace this kind of image classification framework with other kinds of labeled adaptation procedures, as well as unlabeled adaptation scenarios. So we could present the model during this meta training process with all sorts of scenarios that we want it to be able to adapt to, present it with unlabeled data from those scenarios, and train it to be able to adapt to those scenarios and effectively predict the correct answer under that scenario, given some unlabeled data. Such that at meta test time, when it also needs to adapt with unlabeled data, it can apply that same adaptation strategy that it learned in order to understand and handle that distribution shift. Okay, so that's kind of the key idea about what I'll be talking about today. And in particular, I'm going to be talking about 3 different instantiations of this. First, I'll be talking about whether we can adapt online to new users with unlabeled data, and this will be something more like an image classification and supervised learning scenario. Then I'll talk about whether we can adapt online to new environments, and in particular, allow embodied robots and agents to adapt online. And this will bring us more towards a reinforcement learning setting. And we'll look at 2 different scenarios, one where we can adapt online to different dynamics, and a second scenario where we need to be able to actually explore the environment in order to adapt to that environment. Okay, but first let's look at the more image classification, the more standard scenario, and look at adapting online to new users with unlabeled data from those users. The motivating problem setting here is going to be based on federated learning, where we assume that we have data from lots of different users, and typical standard supervised learning would just kind of lump all this data together and train a classifier to recognize, for example, the handwriting of these different users. However, what we're going to do instead is we're going to actually separate this data out into the separate users that it came from, with the goal of being able to adapt to a new user on the fly using just unlabeled data from that user. And the reason why this makes a lot of sense is that we typically don't want the user to have to annotate the data that they are entering into their phone, for example. And if we can do this on the fly with a small number of unlabeled examples, it puts minimal burden on the user and also improves the system for that user. And so it's worth mentioning here that there are possibly many different target domains corresponding to many different users. And so we want adaptation to be quite fast and efficient. And so this means that things like domain adaptation, where you assume that you have data from the target domain during training, isn't necessarily going to be practical for a scenario like this. We essentially want to be able to adapt very quickly and online at test time to many different target domains. So to approach this problem, we introduce what we refer to as adaptive risk minimization, where at test time we have unlabeled data from a particular test domain, and this could be from a new user, like in the example that I talked about before, but it could also correspond to a different time of day, a different place, and so forth. And we want to be able to essentially adapt our model to that unlabeled data and be able to infer the labels for all of that data. And this would be kind of a batch adaptation procedure, and we'll also consider a more streaming adaptation procedure where you get these data points one at a time rather than all at once. Okay, and then the way that we're going to approach this at training time is to first separate the training data into these different domains, for example, into the different users, and then train a model that can adapt with only unlabeled examples when they're presented with data from a single domain at test time. Now, and we're going to approach this problem with meta-learning, and an important question now becomes is how we can actually adapt a meta-learning algorithm to allow it to use unlabeled data at meta test time and also in its inner loop. And so there's two different ways that we're going to consider doing this. The first is we can adapt the model agnostic meta-learning algorithm to this scenario where we learn a model such that one gradient descent step sufficiently adapts the model to a domain. Of course, we can't run standard kind of gradient descent with a supervised learning loss function. And so what we're going to do here is we're actually going to learn both the initialization as well as this learned loss function such that the adapted network is well adapted to each domain in our meta training set. Likewise, we'll also consider a more contextual meta-learning approach where we compute some sort of context using the unlabeled examples. And then when we make predictions, we consider both the example and this adapted context. And in the simplest setting, it's worth mentioning that this context could simply correspond to the statistics of a batch norm layer. And in particular, this seems like maybe this would just correspond directly to batch norm, but in particular, in batch norm, you typically try to explicitly make your batches uncorrelated with one another. And here you're actually purposely making your batches correlated by having them come from these different users so that when you're given a batch of a single user at test time, you can adapt to the unlabeled examples from that user. Okay. So we evaluated this approach in comparison to standard training, as well as several robustness approaches, including distributional robustness, and an upweighting approach that tries to essentially upweight the groups to the uniform distribution to handle the fact that different groups and different data from different users may be unbalanced during training time. And then we'll compare the three different variants of adaptive risk minimization. The first is with a context variable. The second is where the context variable corresponds to the batch norm statistics. And the third is MAML with a learned loss function. Great, so the first experimental domain that we'll look at is this federated extended Mnist example, and we'll compare to the comparisons that I mentioned before, as well as a federated learning method. And in particular, we're going to be adapting to new users, new people's handwriting using only unlabeled data from those users. And so the results are right here. We measured both average accuracy as well as the accuracy for in the worst case, for the user that the model is performing the worst. This metric is important because we often care about users having a similar experience rather than only some users having be able to recognize the handwriting and other users it falling flat on. And so what we find is in terms of average accuracy, we actually see a 5% improvement just in average accuracy. And then when you look at worst case accuracy, we see around a 10% improvement between models like ERM and this approach that can adapt using the unlabeled examples. And so in particular, if we look at how this actually works, if we give it something that looks like this, an image that looks like this, the ERM model predicts that this is a 2 with a loop. If we instead have data from that user and we give the model, our model, just these 2 examples, it also predicts that it is a 2 because this isn't very much context. However, if we give it all 50 of these examples, it can actually accurately predict that this is actually an A and not a 2 because it can look at, for example, how this user writes other characters. And for example, if you look at this image, you can infer that it probably writes a 2 in this way, and it probably isn't a 2, it's probably actually a lowercase a because it's different from how they wrote the 2. Okay. And then finally, beyond the federated setting, we also looked at these 2 data sets, CFAR-C and Tiny ImageNet-C, that correspond to different image corruptions. And the goal was to adapt to entirely new image corruptions given unlabeled data from that corruption type. And so we trained using 56 corruptions and then tested using 22 disjoint corruptions. And what we found is, again, we also see an improvement in average accuracy, a 3 to 10% improvement, depending on whether it is Tiny ImageNet or CFAR. And we see an even larger improvement, again, in terms of worst case accuracy. We see kind of an 8 to 21% improvement, so a pretty significant improvement in the worst case. And then finally, I also mentioned that these were all of our results in the kind of batch setting where we're given a relatively small batch of unlabeled examples. We can likewise also look at the streaming example where these unlabeled examples are coming in one at a time. This plot is a little bit busy, but kind of the key things to look at are first this black dashed line, which corresponds to empirical risk minimization. And this blue line and this orange line, we see that once you hit only just about 10 examples that you've seen, you start to see improvements over ERM models, especially when you're using ARM with the batch norm adaptation process, which is shown in orange, which gives us around a 10% improvement in this worst case accuracy. We also compare to an approach called test time training in pink, and we also see a significant improvement between test time training and this batch norm adaptation process. Okay, so the takeaway here is that really only a small amount of unlabeled data allows us to actually get a fairly large amount of leverage for adapting distribution shift and being able to adapt to a scenario that changes at test time compared to the scenarios seen during training. So now I'd like to shift gears and talk about the kind of move from this sort of more image classification setting to a setting where we actually need to have an embodied agent act in the world and adapt online to changes in that world. And we're going to start by this in the scenario where we want to adapt to new environments. And in this setting, we're going to build upon the formalism of model-based reinforcement learning. And the way that model-based RL typically works is you collect some data set, you fit a dynamics model to that data set, and then you can plan using that model, taking actions using something like model predictive controller, MPC. And then typically you iterate, you use the data that you collected by taking actions under this model and use that to collect new data, fit and improve model, and so forth. Now, one thing that's nice about model-based RL is that it allows us already to adapt to new reward functions because you can simply plan under a different cost function or reward function. However, it struggles when facing new environments. And so if something about the dynamics has changed, then this model won't necessarily capture those dynamics changes. And so what I'll talk about here is whether we can adapt this model using data that doesn't have any rewards, data that of just the robot interacting in its environment. Can we adapt online, adapt this model online? Okay, so in particular, maybe the robot is going about its way, going about the task through some path, and things about the environment are changing, such as a terrain change or a motor malfunction. We want to be able to adapt to these scenarios online in a continual fashion. And essentially what we can do is we can take each window of the robot's experience and treat that as a task for meta learning. And in particular, train the model such that when it sees this window of experience, it can effectively generalize to the next window of experience. And essentially this kind of online adaptation problem now becomes a problem of few-shot learning, where you want to be able to take these just k time steps and use that to perform k-shot learning to generalize to the next k time steps, for example. And note that model training corresponds to predicting the next state given the current state in action. And so this objective is actually like a fully self-supervised objective. We don't need any reward supervision. We don't need any labels. We just need to be able to observe our states and actions. And so this few-shot learning procedure isn't just going to be performing few-shot learning. It's also going to be doing so in a way that doesn't require any human supervision. And so the tasks are essentially going to correspond to different slices of experience. And then at test time, we will adapt to these slices in real time. And it's also worth noting here that the entire meta training process itself is also more or less kind of unsupervised, because the robot just needs to explore in its environment and learn how to adapt to different environments. Okay, so how do we go about doing this? Kind of a rough sketch of what this looks like is we store our last m time steps in this case. We adapt our model using those last m time steps, and then we take the adapted model parameters and use this to plan, and then iterate this process. Now, of course, if this update procedure of adapting the model is very slow, then this probably won't work very well. And so what we can simply do is use meta learning to learn an update procedure that can very quickly adapt using these only m time steps of experience. Okay, so how well does this work? We tested this on several environments in simulation to start. And what I'll show here is we meta-trained a system across several different environments and then tested its ability to handle new scenarios at test time. And what we'll see here first is a model-based RL system that's just running standard model-based reinforcement learning. And we see that when the environment changes, it isn't able to effectively kind of walk across this, this world. Similarly, we see in this second example, the half cheetah, each of these platforms have different damping factors. So you can think of it as like a pier, for example. And the cheetah also really struggles to get across the environment because it isn't able to adapt to these changes in the environment. In contrast, if we use this meta learning approach, it's a mammal-based approach that it can actually adapt online to just a few time steps of experience. We see that it can actually effectively get across the screen, even when the dynamics are changing in real time. I'm sorry about the videos being a bit choppy here. Okay, and then lastly, because this is a model-based reinforcement learning approach, it's quite efficient and much more efficient than model-free methods. And this means that we can actually take this approach and apply it on a real robot. And so we applied it on this Velociroach robot. We ran and collected data on many different terrains, trained the model to be able to adapt to these different terrains with just around 8 time steps of experience, and then evaluated its ability to adapt to new scenarios online without any supervision, including a slope, a missing leg, a payload, calibration errors, and so forth. And in particular, if we compare the kind of meta learning approach with an approach that doesn't use meta learning, we see that the approach that uses meta learning is able to kind of walk in a relatively straight line on this slope, whereas the approach that isn't able to adapt online kind of veers off to the right and isn't able to handle the fact that the environment has changed. Likewise, in this last example, we took off the front right leg of the robot, shown here, and the approach that doesn't adapt, understandably, kind of also struggles to stay on the line and veers off to the right, whereas the approach that uses meta learning is able to adapt online in real time to this missing leg and roughly follow that straight line. Okay, so the takeaway here is this sort of self-supervised model adaptation allows the robot to adapt online to new environments without any supervision. Great, so this is fairly effective for different dynamics changes. However, one thing that this approach can't handle is it doesn't reason about whether it needs to explore. It's always planning with respect to its reward function. And if it actually needs to explore in order to adapt to an environment, then it won't be able to effectively explore. It will simply just try to execute on the reward function and exploit that reward function rather than figuring out what environment it's in, for example, and using that information to better adapt. And this wasn't really a problem in the case of different terrain changes and so forth, but in other scenarios where, for example, if you're in a maze or something like that, and you actually need to explore the environment in order to solve it, this sort of exploration will be critical. And so the most common approach for adapting to different environments in ways that require exploration is to essentially just try to end-to-end optimize your exploration strategy and your execution strategy with respect to the reward of actually solving the distribution of tasks. And unfortunately, this sort of approach is actually quite difficult for scenarios where exploration is rather non-trivial. And the reason for this is because of this chicken and egg problem that comes up, where if you are trying to learn how to solve the tasks, that requires you to have been able to explore the environment in order to identify important information for solving the task. And likewise, if you want to learn how to explore, this requires kind of good gradients for having known how to solve the task in order to learn what things are important about the environment. And so in particular, if you imagine a kind of kitchen scenario where you need to be able to find ingredients in order to adapt to a new kitchen and then cook using those ingredients, if you haven't found the ingredients yet, then it's going to be pretty hard to learn how to cook using those ingredients. And likewise, if you haven't yet learned how to cook, then any sort of exploration strategy is going to give you low reward, regardless of whether or not that exploration strategy was good and successfully found ingredients or whether it was bad. And so essentially there's this coupling problem between learning exploration and learning execution. And this makes it pretty difficult for this sort of end-to-end approach to actually effectively optimize both the exploration strategy as well as the adaptation strategy. So how can we go about solving this problem? So we can actually decouple these two things, the exploration strategy and the adaptation strategy, using that information by trying to acquire a representation of the task relevant information. And in particular, the first step that we'll do is essentially learn how to solve the tasks by conditioning on just a one-hot identifier for each environment. And this will allow us to identify kind of the key information that's needed to actually solve those tasks. And then once we have this representation that's needed for solving the task, we can then learn how to explore by training a policy to explicitly uncover that information. And that can be done by simply trying to train a policy to maximize the mutual information between the trajectory that it led to and the representation of the task. Then at meta test time, we can simply run the exploration strategy, the exploration policy that we trained to recover this task relevant information, and then pass that into our execution policy to solve the task. So we refer to this approach as decoupling reward-free exploration and adaptation in meta reinforcement learning. And note that this exploration approach doesn't actually require any rewards if you're trying to adapt to different environments. It's simply going to simply going to explore in a way that allows it to uncover this task relevant information, which is in particular corresponds to information about the environment that's necessary for solving the task. And so we looked at this environment where essentially the robot needs to navigate to a particular object, and the object that it needs to navigate to, the color of that object is indicated on this sign. And so what it needs to do is it actually needs to explore the environment kind of by walking around this barrier and looking at the sign, and then using that information to go to the correct object. And it receives pixel observations as input and just a sparse binary reward. And so learning this exploration strategy can actually be pretty difficult because of these challenges. And so what we find is this is the kind of exploration strategy that it learned, where it learns to go around the barrier right here and then look at the sign on the wall and see that it says blue. And then once it sees this exploration strategy, can infer the relevant information about this environment, namely that it should go to the blue object, and then it goes to the blue key. And so if we compare performance with this approach as well as compared to other meta-RL approaches, we see that it's able to achieve near optimal reward for this environment. And these existing approaches really struggle because of the coupling issue that I mentioned before. And alternative strategies like Thompson sampling also struggle to solve this task. So this pink line corresponds to an upper bound on what Thompson sampling is able to do. Great. So to wrap up, I talked about how we could allow systems to adapt with unlabeled data, starting with an example where we wanted to adapt to new users with unlabeled data, and then ending with examples where we wanted robots to adapt to new environments, including these new dynamics, as well as environments with different signs on the wall, in order to effectively solve tasks and changing scenarios. I'd like to thank my students. If you're interested in learning more about meta-learning, all the lecture videos for my course are available online, and happy to discuss, and also happy to, I'll join the first part of the panel discussion as well.
Thank you, Chelsea, for your talk. And so I invite all the people present here to ask their questions to Chelsea before starting the actual panel that will be chaired by Fabio instead. Maybe I can start with a simple question just to break the ice. Something that I always wanted to ask you, actually, Chelsea, and what do you think about the relationship between meta learning and continual learning? Do you see them as one part of the other, two different, completely different things? What do you think?
Yeah, so I think that their relationship can depend on how you want to use meta-learning techniques. I think that one example is I think that meta-learning can be useful for continual learning to learn continual adaptation strategies. And that's somewhat similar to what we saw in the examples that I showed at the beginning, where we learned an adaptation strategy that allowed us to adapt online and continually from streaming examples. And so that's one way that meta-learning can be useful for this sort of online adaptation. And likewise, I guess the other examples that I talked about as well, where the robot was adapting online to its environment, this is essentially meta-learning for this sort of continual learning. And then the second way that I think that they could relate to each other is you could also use meta-learning within a slice of the continual learning problem. If you have, for example, a sequence of tasks that you're trying to learn, then you can essentially take your experience that you've seen so far, learn how to learn from that experience so that when you see the next task, you can more quickly learn that task. And so we can either view it as, let's use meta-learning to allow us to do continual learning better, or we can use it as kind of a subroutine within a lifelong learning system.
That's great. Thanks, Chelsea. Any other questions before starting the panel?
May I ask one, maybe? I don't want to take up anybody's time. But in your experiment, Chelsea, your environments change in sort of discrete, abrupt steps, seems to me, right? In the different sections of the floor, you take the leg away from the robot, Whereas in your diagram, you were like kind of selling this as a way of gradual adaptation to gradual changes. Do you have experiments that show that sort of capability as well?
Yeah, so I don't have any videos in particular in this setting, but one of the things that I'll mention first is if you adapt fast enough and the gradual change is slow enough, then you can actually use this kind of approach to adapt to gradual changes because basically if you discretize small enough, the gradual change will look relatively stationary on a short time short time windows.
Piecewise linear kind of approximation.
Yeah, essentially a piecewise linear approximation, exactly. And so that's one thing that we found here, and we actually, in a follow-up paper to this, we did actually test it on scenarios that were more gradually changing, like with different slopes and so forth. And we did find that that approximation was actually fairly reasonable. We also have work that I didn't get a chance to cover in this talk, where we actually try to anticipate how the environment is going to change. And we use a continuous latent variable to represent the state of the environment. And that can also very naturally handle continuous changes in the environment. We still use a time discretization because that's fairly common in any sort of reinforcement learning, but it can handle fairly smooth changes.
Thank you.
We have a question in the chat. So maybe we can ask this question, answer this question before starting the panel. So is there a strict definition of online setting? Most exciting work refers to this as use each data only once for training, or data come in sequentially in stream.
Yeah, I think this is a good question. I think that I'd probably take a more liberal definition of online based on what's practical. In this particular work, we do actually adapt to any given time window once, but we do have an overlapping time windows. And so for any given data point, I think we typically adapt to it around 8 times because our window size is 8 and we use a sliding window. 8 seems, and that's something that is practical given the computational constraints that we have here because we're doing this in real time. Also with this federated example, I think that we were storing up to 50 data points at a time. I think that other people sometimes constrain that to be only 1 data point at a time. I like to think generally in very practical terms because problems like robotics are hard enough without introducing extra things that make them even harder. And so I think that if we can basically have a fixed budget for the amount of memory that we're storing in this sort of real-time adaptation, that's what's practical on robots. Likewise, in any sort of really lifelong setting with robots learning multiple tasks over time, I also tend to take a fairly kind of practical stance to lifelong learning methods, where if we have a hard drive available and compute isn't as much of a bottleneck compared to actually interacting with the environment and collecting data in the environment, then I think that in those kinds of problems, storing data is less of a challenge. It's more about trying to transfer to new scenarios and so forth. That said, there are also, of course, scenarios where storage is a huge bottleneck if you're receiving frames at like 60 frames per second or something. And so I think that it's worth being fairly flexible depending on what that application demands.
Great. Then one last question regarding the second part of your talk. Do you think that your approach could be used to reduce the discrepancy between simulated and realistic environments? Or does the distribution chain need to occur while the model is deployed?
Yeah, that's a great question. I don't think that I have a slide on this in this talk, but we have actually used meta learning across different simulated environments to adapt to new environments. That was actually in a way that was very similar to this, except we did all of the training and simulation and then tested in the real world. And we have had actually a fair amount of success with that. That particular paper was by Yusheng Yang and Richard Song. And it was called like Rapidly Adaptable Legged Robots. if you're interested in looking that up.
Perfect. Then thank you so much again, Chelsea, for your presentation and your talk. And I let now Fabio start with the chairing of the panel.
Thanks, Vincenzo, for chairing. Thanks, Chelsea, for your great presentation once again. Yeah, I mean, the last part of the workshop, we decided to devote to a little bit of an open debate about what we think. People gathered here think is the future of continual learning, or it's likely future evolution. And I would like to start this from, trying to gather some sort of consensus from what you guys said, especially the invited speakers throughout your talks. And I think I've identified a number of common points. Like I was mentioning to Tina beforehand, current limitations of continual learning are quite clear. They're like too much attention to like toy data sets that I'm not sure how much information you can extract from, and in terms of setting an agenda for the future. So the need to move towards large-scale experiments and more realistic experiments as well. A lot of focus on supervised learning and especially classification, although things are starting to change recently, and I think that should be encouraged. And need to focus more on streaming data. A lot of your talks were about learning in an online setting, and including Chelsea's, but also things like another recurrent thing was the need to overcome this IID assumption, and I thought I totally agree with that. That's what I said to Razvan after his talk, that the whole point of continual learning, I mean, I'm a relative newcomer to the field, so my main expertise is in the mathematics of uncertainty, really. But from what I've seen so far, I mean, the whole point of continual learning seems to be moving beyond this IID assumption, which is the foundation for most of machine learning in its sort of batch learning interpretation. So I wonder what you guys think is the most important aspect to address going forward. One other thing that Razvan mentioned in his talk is that continual learning is some sort of an umbrella term, right? That kind of is a composite field that encompasses many different learning settings, including the new one that we are trying to propose with this workshop. So how do we address that going forward? Is there a possible route to unification, or what do you think are the most important aspects moving forward? Don't be shy, anyone, and there's no stupid questions to ask or things to say. Maybe Razvan wanna start.
Okay. I guess I've been thinking a lot about sort of unification of all of these things, and I actually don't think we need to do that. I think there is nothing. What we do need, though, is sort of to have a bit of clarity of what are the different types of continual learning / meta learning, or however you want to partition the space. There needs to be a bit of clarity, of like a taxonomy of like what are the different approaches, and a bit of understanding of why those approaches are important, right? Because sometimes it's easier to ask the question, what would happen if at this stage I would do, I don't know, unsupervised learning instead of supervised, and now I have a new paradigm because I've switched modalities or whatnot. But like you need to have a bit of a motivation of why that is happening. So we need to have a bit of understanding where these different forms of continual learning need to go. But I don't know whether we need to collapse them into one. I think it's fine to have multiple. As long as, yeah, I guess that was one thought. And then the other thought that I had, I mean, I don't think continual learning is sort of a problem that we will solve anytime soon. It's just sort of like a big, in my mind, it's a big umbrella term that people are going to work on it for the time being, for a while. And in that sense, definitely going to scale is important. But I still feel like there's some things that can be figured out in toy regimes. And I wouldn't necessarily say that we need all to move. Like, basically, if we go back and think about the ID assumption and we want to get rid of it, I feel like there's some room for theory there. There's some room of like very controlled settings where you can check, you're looking at the dynamics of HGD and you're trying to alter HGD, or you're trying to replace HGD by a different learning rule, and you try to understand how that works. I don't think you can do that at scale in, I don't know, a huge video data set. I mean, the only way you could get things to work is to stay as close as possible to state of the art and make minimal changes. Because, if you take a ResNet and you change HGD with a different learning rule, you're going to have a hard time to kind of figure out whether things work. You need to get there in the long term, but like you need to start in some. We need to allow for more theory people, and we need to allow for also for the toy, but they need to be done with purpose. Like just doing a epsilon improvement of an existing method and just running it on split CFAR, that we shouldn't accept as a paper. But if there's like a theoretical reason, or if there's something specific that is looked at that makes sense to be done in a toy setting, then we should allow those papers to be published. And yeah, I don't know if this makes sense, but yeah.
I think, before anybody else has time to reply, I think I agree with what you said in terms of these two directions are these two things pull in different directions. So like the push towards large scale goes against, to some extent, a better understanding of how we can model data streams, streams of data points that are generated by time varying probability distributions. So continually varying domains over time, and probably working on, I wouldn't call them maybe toy data sets, but controlled problems would help in that respect. So, and I also agree with what you said about taxonomy versus unification, because there are so many different possible protocols and contexts for continual learning, including the one we try to propose with this event, in which you have this. The strong motivation for us was, the realization that in practice in the industry, really you have an awful lot of supervised data at the beginning. You can play around with your TPUs or like 64 GPU servers, but then after that, you basically only have unlabeled data points, and you need to deal with them with very limited computing power. So among the continuum or all possible continual learning settings, we thought this was a very real, particularly realistic one, that really reflects real world requirements. And I think Tina said something like that the inspiration for the theoretical analysis of different possible or alternative definition of continual learning should come probably from real world problems.
I can comment on some real world problems. I've been doing this for a while, and I've tried to get some practical application going. For example, I talk about this dialogue systems. So when you have dialogue systems, you have a very typical of class continual learning problem, because you want to add more skills. So for example, now you can answer questions related about weather, and tomorrow you can do reservations, and tomorrow you will add more and more, because typically with a commercial system, they have a few hundred skills. So if somebody wants to add a new skill or a set of skills, and then essentially you have to do a classification of intent. When the people ask a question or want to say something, you need to understand which domain is he actually talking about. And we want to have this, I try to have this saying, you can incrementally add a new skill, but it's just impossible to be added. The reason is forgetting problem. And although we have been solving these toy problems, but we can't even solve the toy problems. The real life application, as far as I know, those reasonably big companies, they have a few hundred tasks. And then they want to add more. And that's just incredibly difficult. And if you say you are going to have the accuracy drop, then they will say no. I mean, accuracy cannot drop. It has to be 95, 96 above. And if that's not the case, then forget about it. So this is the one situation. And we are doing some research on this, but obviously it cannot be practically used. Another situation was sort of what you were talking about, the time variant kind of data. For example, in recommendation systems, which is very typical. And so the fashion changes. Tomorrow, people like blue. Today, people like pink, and things change. So you want to update your model constantly. And so in the company, what do they do? I mean, depend on the application. Some application says I update every day. I rerun the model completely. And some do in a week. So depend on how fast the speed is changing. The problem is, in this case, is really very nice application for sort of continual learning, because you get class labels automatically. Because if you recommend the guy to buy this blue jeans, but the guy didn't buy, or they bought something else, you can also see other sort of jeans become popular. So you got this data. And so you don't really need to get somebody else to give you a labeling, and you have to stop the system. The problem is still this forgetting problem cannot be solved. And if you don't solve this problem, the company cannot use it. And so that's my experience. Of course, in natural language, it's the same kind of situation. And so it's not just we are solving sort of toy problem, that the real problem is really large. For example, I work with this sort of, I'm not really formally working with them, but just talking with them about the situation, and try a little bit, try a subset of the data. So to become games, the recommending games. And it's just, they can't use it because it's forgets. And the accuracy is gonna drop. You try, replay technique, whatever techniques, and it's going to drop. When it's dropped, the company said that's you can't do that.
Isn't that because, I mean, like Tina was saying, all these objectives are like contradictory in themselves. I mean, they don't work in the same direction, so you cannot have them all, basically.
Not really. I mean, this
is
just one thing, right? It's very clear problem. For example, this is intent classification, right? You have so many tasks you can do. You can book hotels, restaurants, whatever this dialogue systems. So I add one more, car repair, for example. Then you can't add because you're going to forget slightly. Of course, if you're adding only one task, you're not going to forget a lot. But if you keep adding a few more, that's going to forget. And then the company can't accept this.
But isn't the very notion of task an artificial? Sorry, Vincenzo. Isn't the very notion of task an artificial one? I mean, I can see.
No, these are real. These are very real.
In your problem, in this sort of problem, like a dialogue system is a real one. But in a lot of other contexts, there isn't any task subdivision, and that's artificially imposed on the problem.
Yeah, it's true. For example, as I said, that the recommendation has no task division. It's just recommendation, and can you recommend accurately? Because of fashion change, you have new products comes in, you have old products goes out, and every day is changing. And some company have to update every few hours, some a day, a week, because they want to get it accurate. So if we can do this continual learning to get this system become autonomous, can update it by itself, that would be great.
Yeah, Bing, I wanted to ask, but do you have some insights on why replay techniques that we know are working well on many scientific academic problems that we are facing are not working in these particular settings? Because I would have expected that, at least using a large replay buffer would solve even those more large scale.
Yeah, we tried 5%, 10% replay buffer because the commercial data normally is pretty large. 5% is a lot. They're talking about a few thousand. It's not just like what we do research, 20 data points. Even in that case, and the first task you forget a little bit. The second task you forget a bit more.
But this is very interesting because I don't think there is like a lot of scientific evidence that replay is not working in some cases. I don't know if I'm not aware of this.
It helps, but the problem is it's not up to the industry standards. Right? Because they can't accept. For example, we did two things. One is the sort of intent classification. Another one is the sort of extraction task, sort of try to extract those slots. And the extraction of slots is pretty okay. But the reason is because all these tasks, I mean, the same kind of entities. So you can, when you do this for replay 5%, we use actually 5%. And it was okay. I mean, it's not forgetting, but the intent part is forget. Quite bad.
I think Tina wanted to intervene here. Did you?
Okay, go ahead.
Yeah, I just want to refer to like the paper we have at ICCV where we look at the replay. And indeed, our findings is that there is some overfitting going on. And so indeed, the way you learn, actually, the dynamics push you towards really the boundary of your flat minimum. And so there is always some overfitting to your buffer, and so some forgetting is inevitable if you just apply replay the way we usually do it. And so, yeah, how bad that is, of course, depends on how different the tasks are, how big your buffer is, and so on. But so, yeah, in that sense, it doesn't come completely as a surprise to me.
One thing that I'll add here is I actually teach a lecture on lifelong and continual learning in my course. And one of the things I actually have the students do is I give them like a list of 6 different applications. I tell them to pick one of them and think about the things that they really care about in that application. And they're completely different across different applications. In some applications you have task boundaries, and others you don't have really any explicit task boundaries. In others you like, maybe you have no storage, and some you might like storage is not at all a bottleneck and it's more data that's a bottleneck, and you can just store everything. In some examples you really care about forgetting, in other examples it's actually good to forget because maybe the kinds of things that you saw much previously are different than the kinds of things that you're going to see now. And so I think that when thinking about the continual learning problem, it's I think that like continual and lifelong learning refers to all these sorts of things, and it would be helpful to have potentially a taxonomy. I think it also just is important to be open-minded about the different kinds of problem statements that different applications demand.
Isn't there maybe a lack of that? Because one of the things we found out when we tried to understand how to formalize this problem was that there wasn't really, in a lot of cases, there isn't really a proper formal definition for the problem in terms of, you know, what the goal really is, what training protocol should be, how the data should be visited, what the testing protocol should be. And that's part of the effort that we put in for this continual semi-supervised concept. And I think something like that should probably go happen for a lot of other subfields of continual learning if we want to get this sort of taxonomy in place at some point.
Yeah, I think that makes sense. I also think that in general, a paper on this topic should probably lay out the particulars of the problem statement that paper is considering, because it may be different than other papers. And I guess I've had situations where we do that, and then the reviewer says, like, why aren't you addressing, like, why don't you do anything to address forgetting or whatever? And it's like, well, data storage isn't the bottleneck, or maybe we want forgetting or something like that. And I think that having more flexibility in those and being more open-minded to different problem statements and laying out what those problem statements are and motivating why they make sense is important for the community.
There are bad reviewers and good reviewers, right? And also, I mean, personally, I really think the problem statement should always come first in a paper, like, you know, first to identify what problem you want to solve and why. And then you tell people how you do it. You don't just jump into it like, I'm going to propose this sort of new model for some random reasons that tackles a problem I haven't really properly defined. I don't really like those sort of papers personally, but you know, that's a matter of preference, I think.
I have a question / comment, I guess, to follow up. It's kind of related to what Bing was saying, but it's maybe related to what Chelsea was talking about it as well, or part of Chelsea's talk. Another industry perspective and how much they really don't want models to get worse on kind of existing data that they've seen already. So for example, in Chelsea's task, the handwriting work, we often have problems where we want to adapt to a particular user and provide better accuracies for that person's handwriting. But at the same time, the company will often say, well, how well does it perform on the kind of for the people that were in the meta training data set? How much does performance degrade? And if it degrades a lot, the company is, they don't like that. So Chelsea, have you tried any experiments to look at like for those adapted models, how well they do on kind of the people in the meta training set, or do you have an idea of how you might ensure that it doesn't drop off significantly?
Yeah, I guess we were operating under the assumption that you can always like very quickly adapt to different scenarios and then just kind of reset to the old model and adapt again to different users, which can prevent that degradation. But if you do really care about an adapted model also working well for other users that it wasn't intended to adapt for, then you can always add some sort of objective to the outer loop to be not just good at that user, but also good at the other users. I don't think that we explicitly measured it, but I think that I would expect it to be not that much worse than an ERM model when it's adapted to the user, because I guess in the handwriting example, like people's handwritings are still fairly similar, and there are only some small differences, at least in the data set that we are looking at. But I think it probably also really depends on the data set, the application.
Yeah, fair enough. I mean, in some sense, I kind of feel it's unfair to ask this type of question, because it's kind of like you want everything, and like we've been talking about, it's it's kind of, you have to pick what's most important to you, and you can only optimize so many of these things. But on the other hand, it's you can think of realistic situations where it's important, like maybe for my phone, the model is really well adapted for my handwriting, but then I give my phone to my friend, and they try to enter something, and then the handwriting recognition module fails at that point. So it's not outside the realm of possibility.
Lucas had a question.
Yes, so I want to come back to a point that Tine raised in her talk about the mismatch between the settings that we're exploring in academia versus more realistic settings. One thing I'm sort of noticing, especially in the online incremental classification research direction, is that very few of the methods sort of focus on compute, and there's a lot of focus on memory. And I find that a bit weird, especially that if you have like enough compute, you can basically solve catastrophic forgetting. So I'd like to hear your thoughts on potential other mismatches that you think we should address first, and also maybe on how to kind of enforce those as a community when we're reviewing papers and such.
So basically you're saying instead of slow continual learning, you think we should focus more on fast continual learning. That it's because I think it's okay to not focus too much on the compute in the current stage of the research, because you can always optimize code and do clever things that are not the core of the problem. Same holds for memory. You can just say, okay, let's compress our buffer, and by compressing our images, we can save on the memory. But that's not what is the focus of the continual learning research. And so optimizing code or compressing data are things that, we all know that might help, but that's not the core issue. And then I guess indeed it's the trade-off, like we cannot solve them all, and we have to give in somewhere. And so either you give in on memory, or you give in on compute, or you give in on forgetting, and that's what makes it so difficult, that there's so many different axes that you always have to find a compromise, and then it makes it difficult to really compare things and so on. And I guess you can come up with arguments for any combination of weights you put to these different axes. So I don't think there's really like one answer that we should all aim for. And somehow we should allow this flexibility and variability. At the same time, as was already mentioned a few times, it should be clear what your setting is. And it does make it harder to compare. So then it's good to have challenges so that then at least we all focus for a while on the same things and see what that gives.
Just wanted to add that.
Yeah, sorry.
I just wanted to add that for me personally, actually, I think focusing on compute is actually quite interesting, because the way I think about continual learning is sort of this idea that, you know, you've learned several tasks and then you get to build on that knowledge to learn faster. And if you don't look at the compute, if your inference becomes suddenly 20 times more expensive, then you're not really gaining sort of what you're supposed to. Like, it might be simpler to just learn the task independently and have like a big switch if else. But again, it depends on the setting. The bigger thing I wanted to say is that it's not always clear to me that academia and industry need to match. There are really good reasons. So, for example, I want to understand sort of this ID assumption that's fundamental to deep learning. You know, in order to study that in an academic setting, I will not go for the problems that are relevant for the industry. Like, I would need to separate myself and do slightly different things. So, so that's one thing. It's not always clear to me that these things need to be perfectly in sync. The other thing that, because you're talking about what are typical discrepancies. Another issue that I see is in continual learning, like it's been said before, you need to make all of these trade-offs between, I don't know, memory, compute, amount of forward transfer, and so forth. And these do not depend only on the setting. They don't only depend on the protocol and whatnot. They depend on the actual data. So if I'm playing, say, with Pentry Bank or something small like that, and I'm trying to do some kind of construct a continual learning task of it, the trade-offs that would be optimal for that setting would be quite different from a realistic, you know, industry scale language data set that is extremely diverse and has a lot more structure to it. So, you know, sometimes the problem lies in the data that we do. Like, we come up with this algorithm that works so well on tiny ImageNet or I don't know what, but it actually, it exploits the particular data set, and it works because we're running it on that. And in industry, it would not work because the data is different, not the task or the protocol or anything like that. So, you know, that's a discrepancy that, you know, some places can deal with it where they have lots of compute and maybe access to lots of data, but some places cannot. It's sort of up to the industry to kind of figure out that gap, because they have the compute and the data.
So it's a combination of both, I would say. So it's different kinds of problems as well as different kinds of data. So I don't think it's one or the other. One thing that Lucas said that in some other chat box that I found interesting was that, I mean, something that I support is that we should look at modeling dynamics of the data in order to overcome the IID issue. If in an online and streaming setting, one of the really interesting bits, in my view, is trying to find ways of modeling dynamics of the data and the dynamics of the model shift. How does the domain shift over time, and how much information can we gather from the data stream on that?
Yeah, I guess the question that Lucas asked at the end of my talk, where I interpreted it as like controlling the data and then going to curriculum learning, actually, when I read it again afterwards, was more referring to this thing. And indeed, in many practical applications, probably the speed at which your distributions shift is much slower than the speed at which new data comes in. And so in that sense, you could exploit something that you can learn about what domain you're currently in or what setting you're currently in. And in a practical setting, I'm sure that will help to do better. From a theoretical perspective, it's difficult to have a proper formalism on how to model that or incorporate that. So let's say we have split ImageNet or whatever, but then if there we don't have a real distribution shift, it's like a very artificial one, and then making that more realistic and then modeling that is like, I guess, something that's only possible really if you go to more realistic data sets and realistic distributions.
Sometimes
Yeah.
on that point, sometimes you also have multiple different dynamics at different time frames. So this is something that we thought about when considering like surveillance scenarios. So you have abrupt changes, but you also have daily cycles, you have weekly cycles, you have yearly cycles. So, and then the way the data distribution changes is the result of the overlapping of all these 3 or 4 different mechanisms. So one thing that can come from studying real data is understanding the level of complexity of the dynamics of continual learning, of data streams in continual learning, and then what could be the proper theoretical mathematical framework for modeling that kind of dynamics. Whereas if one sticks with artificial settings, it's hard to get insights from artificial settings because you don't really get inspired by these observations, at least in my experience. One other thing, we have around 15 minutes. One other thing I think it came out from the discussion was the fact that continual learning is at least an attempt to mimic a human lifelong learning experience. And clearly, lifelong learning for humans is a combination of, I think Bing stressed that much in his talk. It's a combination of exploring environment and interacting with environments, observing other people doing things. And so it seems to me that true, and also dealing with multiple tasks at the same time, it's too bad that Chelsea had to leave, but obviously the human lifelong learning experience is a combination of dealing with multiple tasks that change over time, supervised learning or based on observation of what other people do and how they behave, and also learning from our interactions with the environment. And the 4th factor is probably being taught. So like logical and sort of knowledge-based information that comes in from your teachers or your parents and so on. So it seems to me like moving, one of the definite direction continual learning should head towards is a better integration between supervised reinforcement learning and possibly even neurosymbolic approaches, so combining neural and learning approaches with more symbolic reasoning. I don't know what you think about that.
I can give you some sort of examples in this kind of situation. For example, I mentioned in the talk also, we do have specific areas dealing with each of these subtopics. For example, how do you detect novelties, the new stuff, and how do you do some interaction with people? I mean, the natural language people are doing that, what is called the grounding stuff, right? And then you also have what we call the continual learning, what we are discussing now. And in this continual learning scenario we are working on in the machine learning, we assume the tasks are given and data are given. So you don't have to get your own stuff. But when you need to get your own stuff, this becomes very difficult. For example, I mean, at least for the novelty detection, I think let's forget about novelty detection. I think that you can do reasonably. Even you miss something, it's probably okay unless it's something critical. For example, self-driving cars, you miss something, and that is going to be terrible. So when you're doing something, for example, natural language, I mean, if you don't understand that guy, you don't understand, it's fine. I mean, just say, I don't understand. And then you can detect for, but when you want to understand certain things, you want to sort of learn that thing, then you have to interact. When you have to interact, you only get a very few examples. You don't get so many examples. So then you got a problem of a few shots learning, continual learning. And that gets very tough because we try to do that and it just doesn't learn anything. And so we have to end up doing something sort of information retrieval kind of stuff. So at least that guy works reasonably. And of course, I mean, people always want to have a deep learning model, but it just doesn't work. So another part of it is, which we have not touched upon, and you just mentioned, is a combination of supervised learning and reinforced learning. The self-driving car has a very specific situation, which is exactly like that. So what happens is, for example, you drive, you see something in front you don't recognize. Okay, so what do? So in our continual learning, they say, oh, let's just learn that stuff, right? But for the car, it's much more complex than that because the car has to respond. When you see something, you got to slow down. You not just learn that, you got to slow down. So when you slow down, you got to learn how to navigate around that stuff, right? Whether you see somebody, let's say a piece of tree leaves drop down, and then you say, oh, I mean, the guy in front of me has gone through that. Let me go through it as well. That's probably is no problem. But if you see a piece of rock or something, you know, you got to respond to that thing. It's not just learn that thing, you got to respond. So the response itself is a learning process. You know, how do I go around of it?
Can I just say something there? Okay, my understanding of how reinforcement learning is used in autonomous driving is not really, it's not really a form of continual learning, because the way this is really done is done by doing imitation learning first from
no, that's not
bunch of drivers, and then running a lot of simulations. So you run a lot of possible simulations on what you think are realistic situations, but that's not really continual learning, is it?
No. Let me tell you why. Okay, let me tell you, I have a real experience. Okay, so once we drove outside, we have the car driving outside. Then the car suddenly stopped. We have no idea what's going on. We manually go to check. There's nothing in front. There's no car. There's no obstacles or something like that. Nothing. And then we have to manually take over. The car doesn't go. So when we go back to check, we find out, oh, there's a little piece of stone, very small. And then the ultrasound or something like that detected, just refused to move. You see, so in this case, if the passenger can help, say, just go ahead, that's no problem, then you can learn, right? So this kind of, there's so many interesting situations where it can be taught.
Yes. So I suppose part of the interaction with the environment can be being taught by human or some other agent.
Yeah, exactly. Another situation is when you sort of I'm going to let's say I'm going to a shopping mall, but you can't say, as a person, I can't tell you XY coordinates, where, right? I mean, I have to tell you, go forward, right? You stop in front of that thing, that kind of stuff. So that gets kind of very difficult. Now you need a dialogue system, and dialogue has to be quite sophisticated. It's a lot of interesting things going on when you try to build a self-driving car, which is practically useful.
That's where the neurosymbolic approaches can be useful, because, you know, if you manage to establish a mapping between semantic concepts and visual entities, then that becomes easier, doesn't it?
Yeah. I mean, it needs a lot of stuff. It's not just, you know, you drive and give you the XY coordinate. That doesn't happen. I go to a shopping mall, I don't know what coordinates I'm going to stop. You have to communicate.
Okay, I think it's probably a good time to head towards a conclusion, because it's getting late and I understand people are getting tired as well. We had a very interesting discussion, very, very exciting invited talks and our presentation that stimulated a lot of discussion. So it's probably time to call it a day. So I would like to do two things. We don't have a proper award ceremony, but I would like to give a shout out to the authors of the paper that won the best paper award, Lucas Caccia and his supervisor, as I understand. And is everybody saying, and the authors? So a little round of applause to Lucas and co-authors for that work, and also to the authors of the best student paper work, Danajit and co-authors. If you're still around, Danajit, you can share your face maybe. So another little round of applause. There you go. So well done for that. So especially your paper, Danajit, was very much in the philosophy of the workshop of the continual semi-supervised learning concept. So that was much appreciated. And in Lucas's case, there was very much an appreciation of the technical sophistication, I think, of the approach using mental learning. So that was very nice. I promise you will have some sort of signed certificate for those via email at some point. So I promise you'll have a piece of paper to show or print. And also you will receive an award of 1,000 Canadian dollars from our sponsor, Huawei, which I think is well deserved. You will have to share it among all the other authors of your respective papers. So that's just 2 for Lucas and I think 3 for Najit. That's okay. And having said that, I would like to thank all the invited speakers, Tine, Bing, and Razvan, and Chelsea for being so kind as to attend and come up with very interesting contributions that stimulated a lot of discussion. Like I said, hopefully this will be just the first of a series of events at future conferences, maybe not IJCAI or maybe ICML or some others. But we feel that this was a good experience and deserves some continuation in the future, especially the push towards more realistic benchmarks, which is agreed by a lot of people who are here. So thanks to all the authors of the accepted papers and all the attendees to the workshop, and hopefully we'll see you next year at some other conference for the next iteration. Thanks everybody, and have a nice weekend.
Thank you.
Thank you so much.
Thanks for coming. Great. Thanks for your time.
Thank you. Thank you.
I hope you enjoyed it.
Bye.
See you. Bye.